So let's work another example where we find the impulse response of a discrete time LTI system. The system that we'll examine here is actually the exact same system that we examined in the previous video. However, in this example here, when we find the impulse response, we're going to assume that we have a causal system. I actually think this problem is quite a bit easier because for a causal system, that means we need to have an impulse response that goes to the right. So our choice for kind of which direction we go in the time domain, whether left or right, is very simple, because for a causal system, you're always going to choose the right-sided time domain signal when you go back to the time domain. So you don't really have to think as much about kind of which direction to go. It's always going to be the right side for a causal system. So we'll go through this just a little bit faster because you've seen all this before in the previous video example. This is the system that we're working with. The transfer function h of z is provided, and it's already been decomposed. So there are 3 poles in the system. One at z equals 0.8 e to the j pi over 4. One at z equals 0.8 e to the minus j pi over 4. And one at z equals a negative 2. Our goal here is the same. We're still going to find the impulse response, but our assumption has changed compared to the previous video where we were finding the impulse response for a stable system. Here in this example, we're going to find it assuming that it is a causal system. So I can go ahead and draw the complex plane and draw the unit circle, and then we can go ahead and draw the pole locations just like we did last time. So this one is at 0.8 e to the j pi over 4. So this pole is 0.8 away from the origin, so it's close to the unit circle, but not quite there, at an angle of pi over 4, which is 45 degrees, so there's 45 degrees. This one is at negative pi over 4, negative 45 degrees, and then the pole there at negative 2. So the exact same setup we had last time. And then the only difference now is we know that the region of convergence has to be outside of a circle, meaning we have to choose right-sided signals in the time domain. So for all of these poles, I'm going to choose a right-sided signal. Pole at minus 2, I'm going to choose right-sided. And then the poles at plus minus pi over 4, I'm going to choose right-sided. Like I said, for the causal system, this choice is a lot more straightforward, I find. So now let's just go ahead and write down what the impulse response is. H of k is going to be 2, do that 2 right there. And then this number raised to the ku of k, plus 2 times this number, that pole location, raised to the k, u of k. And then finally 5 times this pole location, which is a negative 2 to the k, u of k. So all these are now u of k's because they're all right-sided signals. And then as before, if I want to, I can factor some terms out here. These both have a 2. They both have a u of k. They both have a 0.8 to the k, right? So I can factor that out, factor all that out, and then what I'm left with is e to the j pi over 4 and e to the minus j pi over 4 raised to the k. And then this we know is 2 cosine pi k over 4 based on our trig identity. So I'll go ahead and write the rest of that, and then yeah, that's 2 cosine pi k over 4. So the 2 times 2 turned that into a 4, and the rest of this stays the same. So that wraps up this example. We went through it a little bit faster because it's so similar to what we just worked, but we have now found the impulse response, h of k, assuming a causal system, which is a lot easier because for every pole location in the system, you're always going to choose a right-sided time domain signal. So that's it for now. Thanks for watching. In the next video, we'll move on to a new topic. We'll talk about inverse systems. So if I have a system and I want to find out an inverse system that perfectly cancels out that system, that's what we mean by an inverse system. And we'll talk about properties and some new terminology associated with that idea. Thanks all.